All right, so bases hydrolyzed. So when we have some like a compound that doesn't consist of ions, like ammonia, we could still have the potential for ion combination reactions because we know ammonia is a weak base, and weak bases partially hydrolyze. And when they undergo partial hydrolysis, they'll make small concentrations of ammonium hydroxide. These small concentrations can potentially react, and so we have to be aware of that. All right, the next thing is this, ammonia-like compounds. If you go back to chapter 3, you covered some, actually I better write this down. So bases do not ionize. They hydrolyze. All right, ammonia is one common one, but there are others, and the others are the organic class of compounds called the amines. The amines, A-M-I-N-E-S, are ammonia-like compounds. And so if we take nitrogen, which sits at the center of ammonia, but instead we bond it to other species, which we'll call R prime, R double prime, R triple prime. This is where R is equal to hydrogen or carbon. It turns out hydrogen has electronegativity of 2.1, carbon has electronegativity of 2.4. 2.1 and 2.4 are very close, 2.4, 2.5. And so these two have about the same electronegativity, which means that, the bond polarities and electron cloud distribution is quite similar, whether this is a carbon or a hydrogen. And so what we'll see is a compound like this. For example, where we take the hydrogens and replace them with methyl groups, CH3 groups. This compound is called trimethylamine. And trimethylamine, whether it's carbon or hydrogen bonded to the nitrogen, it really doesn't change the electron cloud that much. And therefore, this is going to be a weak base, just like ammonia. And so when we have something like this, then trimethylamine or dimethylamine, or we can add ethyls or whatever else to there, propyls, isopropyls, butyls, is going to behave the same. So if we take trimethylamine, CH3,3N, and react that with water, we expect to form some, weak bases form, when they hydrolyze water, what do they form? Well, when weak bases hydrolyze water, they are going to form, the weak base is a proton acceptor, water is a proton donor, it's going to form trimethyl ammonium ion and hydroxide. And so this is just like ammonium ion, except we have methyls instead of the hydrogens and hydroxide. And so weak bases hydrolyze water to form hydroxide. And the stronger the weak base, the more hydroxide. The weaker the weak base, the less hydroxide. Strong bases hydrolyze water completely. Strong bases are strong electrolytes. Strong electrolytes hydrolyze water 100%. So you heard of the leveling effect of strong acids, right? Well, what do you think about the leveling effect of strong bases? It's the same thing. There's going to be a leveling effect of strong bases because all these will hydrolyze water completely to form hydroxide. And they're all going to form the same amount of hydroxide, even though some of these bases are stronger and can more easily pluck off the hydrogen or the proton off water. But all these are strong enough to pluck all the hydrogens off for themselves. And so once they react, then we're left with hydroxide. And so we come up with one more statement, and that is this. The strongest base that can exist in water is hydroxide. All these bases here will react or hydrolyze water 100% in the process forming hydroxide. And so let's look at just one, example. The strongest acid, what's the strongest acid that can exist in water? The strongest acid that can exist in water is hydronium. And so even if we have HCl and HNO3, those aren't going to exist. Both of those are going to react with water 100% to form hydronium, and all we're going to be left over with is hydronium. And so it's going to form the same amount of hydronium. Just like the strong bases will form the same amount of hydroxide. The only exception is oxide. For every mole of oxide, we form 2 moles of hydroxide. But otherwise, all these, sulfide will form 1 mole of hydroxide, amide will form 1 mole of hydroxide, etc. And so we have the leveling effect of strong bases and the leveling effect of strong acids. Okay, that's the caveat of using this table. And then as we get to weak bases, then they're ranked according to how much hydroxide they produce on hydrolysis of water. And so the stronger, something like carbonate stronger than cyanide. That means carbonate produces more hydroxide than cyanide in water. All right, so we're looking for favorable ion combinations, and so we have to worry about the amines and ammonia because those can create ions. And then we look for these ion combinations, and what we look for is this. Let me back up. We look for precipitations, and so ammonia is notorious for precipitating out hydroxides because we form some hydroxide when ammonia hydrolyzes water, or any of the other amines. Any of the other amines have the potential for precipitating out hydroxide. So let's review some of the solubility rules. Not only do we have hydroxide precipitates, but we can have a whole slew of other precipitates. Then solubility rules, we have the solubility rules from chapter 5, which I don't like as much as the solubility rules from your lab manual in Chem 1A. And so let's go back and review the solubility rules from your lab manual in Chem 1A. And that is, 1, we look at the cation first. Group 1 and ammonium compounds are all soluble. Okay, after we look at the cations, then we switch to anions because it's just easier that way. We go to anions and we look at nitrates, acetates, and chlorates are all soluble. And then we go to chlorides, bromides, and iodides are all soluble except for silver, lead 2, and mercury 1. And then we go to sulfates. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. And so those are the primarily soluble anions. And then we switch to the primarily insoluble anions, starting with hydroxides. Hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. Well, group 1, ammonium, calcium, strontium, barium are the strong bases, the hydroxide bases, soluble hydroxide. And then we go to sulfides. Sulfides are all insoluble except for group 1 and group 2. And then we go to carbonates, phosphates, and chromates, which are all insoluble. We always look at group 1 and ammonium first. And so review the solubility rules. I assume everybody had to memorize those, right? You have to memorize the solubility rules, but you don't have to memorize this. Now some people ask me, do you have to memorize this? No, you don't have to memorize this. Later on, what you want to do is you want to look for patterns of reactivity because we want to understand this more from a structural and compositional standpoint. That way, if an acid doesn't occur on this list, what if an acid doesn't occur on this list? You have 2 answers you can give the instructor. If the acid doesn't occur on the list, you could say, hey, we never saw that before. That was not on the chart, right? Or you could figure it out based on structure and composition. This acid is very similar to that acid. And therefore, based on that, I would expect it to be ranked around here. Which answer do you think they're going to like better? You know, obviously the second one, because it shows you can think a little bit deeper about this than just is it on the table or not on the table. But you don't have to worry about this because this chart will be given on tests here. Not the whole, not this. You need to read the footnotes. You should read the names. But just this center part here, we have the acid and base pairs word. All right, so we look for the acid strength. We don't memorize those. These are ones we do have to memorize, though, the gas formers. Which, this is still on, yeah. The gas formers, so for example, if we have hydrogen ions and carbonate, we get a good ion combination called carbonic acid. But the thing about carbonic acid is it's unstable. What does carbonic acid spontaneously decompose into? Water and carbon dioxide. So we wouldn't write it as carbonic acid because we know it's inherently unstable. We'd always write water and carbon dioxide, not carbonic acid. The same thing goes for sulfurous acid. Sulfurous acid decomposes into, yeah, water and sulfur dioxide. Ammonium hydroxide. Ammonium hydroxide decomposes into ammonia and water. H2S doesn't decompose. H2S is normally gas. It's a toxic gas. It's hydrogen sulfide gas. The thing about H2S is it's easy to detect. You can smell it at the part per billion level. It smells like rotten eggs. The bad thing about it is it fatigues your olfactory sensors so that pretty soon you can no longer smell it. And so you can be exposed to lethal levels of H2S and not even know it's present. So if you do detect H2S, you just move to fresh air immediately. Unfortunately, somebody got a lethal dose of H2S in Ventura, ended up dying in one of the oil fields there. HCN. HCN is normally a gas too. This is bitter almond gas, hydrogen cyanide, very toxic. And so you've got to watch out for these ion combinations. You never want to mix sulfide-containing compounds with acid because H plus and sulfide make H2S. You never want to mix hydrogen ion-containing compounds with cyanide-containing compounds because if you mix hydrogen ion-containing compounds and cyanide, they like to come together. The hydrogens like to come with the cyanide. In other words, don't mix acid with cyanide salts. Mix acid with cyanide salts, you're going to be generating HCN. You could, we used to have cyanide salts in Chem 1B, but a lot of people didn't pay attention to this and they mixed acid with the cyanide salts, generating HCN gas in the laboratory, so we had to get rid of them. But at one time we had them. All right, so those are things we look for in driving forces. You know, precipitates, stronger acid, weaker acid, and gas formers. So let's take a look at some sample metathesis problems. Here. For metathesis, we want to write three types of reactions. We want to write the CE, which I take for complete equation, the IE, the ionic equation, and NIE, the net ionic equation. Not only do we want to do that, we also want to state what the driving force for the reaction is, like we did for this over here. So let's try this problem here. Calcium carbonate. What's the formula for calcium carbonate? Ca, CO3, plus sulfuric acid, H2SO4. This is just your AB plus CD double replacement reaction. What does it form? It forms calcium sulfate, and we just switch the ions, the ion partners. That's it, and see if they like each other. So calcium sulfate plus. Now this is tricky because you know, carbonate can accept either one hydrogen, so it could be HCO3 minus, or it could accept two hydrogens to become carbonic acid. So what should we do? Should we give it two hydrogens or one hydrogen? We're going to give it two hydrogens. And so for metathesis, assume complete reaction. Do complete reaction. And so we end up with that. Now, we know something about carbonic acid. Is carbonic acid stable? No, it's unstable, so we should never leave it as carbonic acid. Really, if we form carbonic acid, it's immediately going to decompose into what? It's going to immediately decompose into water and CO2 gas. And so this would be the correct equation. I wouldn't want to leave it as carbonic acid, because carbonic acid, if somebody asks you, oh, give me a bottle of carbonic acid, they aren't going to be able to give you a bottle of carbonic acid. They're going to be able to give you a bottle of CO2 and water. There's going to be a tiny bit, maybe a tiny bit of carbonic acid in there, but mostly it's going to be CO2. All right, the next thing is, before we look at balancing it, is there a driving force? So we look for precipitate formation. So we go to sulfates. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. Well, calcium. Calcium's an exception. So sulfates are all soluble except for calcium sulfate. That means calcium sulfate must be a solid. So we say, okay, that means there's a driving force. The driving force is what we can say precipitation of calcium sulfate. Is that correct? Yeah, this looks correct. We should have a driving force, which is the precipitate of calcium sulfate, except this is Chem 1b, not Chem 4. In Chem 4, you would have been done. In Chem 1b, we'd like to make it a little bit more advanced. And that is, in Chem 4, you would have always been given aqueous, and then a precipitate. But there's a problem here, because carbonates, phosphates, and chromates are all insoluble except for group 1 ammonium. And so therefore, this is a solid. And so this is a very unusual reaction, because here, we can think of reactions as being competition between the forward reaction and the reverse reaction. Which side is more stable? Is the left side more stable or the right side more stable? And so this is why sometimes you can look at this as here. If we go forward, we precipitate out calcium sulfate. If we take this reaction and reverse it, we're precipitating out calcium carbonate. So what's a better precipitate? Calcium carbonate or calcium sulfate? Or is this the leveling effect of precipitation? Could we have a leveling effect of precipitation, whereas here we sacrifice one precipitate or solid to make another precipitate or solid, and therefore it's a tie? Should we call it the leveling effect? The other way to look at it is which one's a more stable solid? You know, since they're both precipitates, are all precipitates the same stability? For example, diamond versus graphite, they're both solids. They got to be the same stability. Is that right? No. Whereas the leveling effect is different. The leveling effect is it's all hydronium. And if you have the same amount of hydronium, it's exactly the same, right? The leveling effect is different. And so there's no leveling effect here. And therefore, this is not really, we don't know. Because here, it could be a tie. We're giving up one precipitate to form another, or one solid to form another. But we need to use more advanced analysis of this, you know, and that more advanced analysis is maybe we need a little bit of theoretical, you know, unless we didn't see a chart, did we? No, we didn't see a chart for the stability of these. And so as far as theoretical, we go back to chapter whatever it was, chapter 12, and we look at ionic lattices. Do you remember ionic structures? Ionic lattices. And so these ionic lattices, which one do you think would have a more stable lattice? Calcium carbonate or calcium sulfate? Well, that's still hard to answer, and so you gotta think back to ionic lattices and think back at, what compounds had very high lattice energies. What were the characteristics, or what thing in common did all the compounds that had very high lattice energies share, as far as some kind of feature, or what did they all share? High lattice energy compounds versus low lattice energy compounds. Well, let me take a step back further. What is lattice energy? You guys recall? You probably recall doing maybe something like the Born-Haber cycle and adding up a whole bunch of numbers and getting the lattice energy, delta H of lattice. You remember doing something like that? Okay. The next step is looking at the pattern of numbers, the pattern of lattice energies. Why some compounds had higher lattice energies and some compounds had lower lattice energies. And so we could look at some, calcium carbonate and calcium sulfate would be a bit more difficult than looking at something like this. Let's look at something like calcium chloride versus calcium bromide. If we look at calcium chloride versus calcium bromide, both are ionic compounds. They're going to have some kind of ionic lattice. Or actually, this is still too complicated. Let's make it even simpler. Sodium chloride versus sodium bromide. In the example in the book, they show how to calculate the lattice energy of sodium chloride, right? What would you expect to have a bigger lattice energy, sodium chloride or sodium bromide? Sodium chloride should have. Why? Why would sodium chloride have a bigger lattice energy? Yeah, exactly. It has to do with the ionic bond. The ionic bond between sodium and chloride is going to be stronger than the ionic bond between sodium and bromide. Why? Because of Coulomb's law. If we look at the distance between the center of charges, this is further apart, this is closer together, or we look at the charge density. Here, in chloride, the negative charge is concentrated in a smaller volume, therefore it has a higher charge density. In bromide, it's spread out, and the more you dilute the negative charge, the less reactive it's going to be. So the more concentrated so this is going to have a stronger ionic bond. Now let me ask you this. In 1 mole of sodium chloride, how many moles of bonds are there? In 1 mole of sodium chloride, true or false, there's 1 mole of sodium chloride ionic bonds. True or false? So if I have 1 mole of NaCl, that means I have 1 mole of sodium ion, chloride ion, ionic bonds. True? Or false? If I had 1 mole of HCl, how many HCl bonds do I have? 1? How many bonds do I have? Just 1 bond. If I have 1 mole of sodium chloride, do I just have 1 bond here? Yes? No, this is the difference. This is a molecular compound. It doesn't form a lattice. When we form a lattice, each sodium is going to be directly bonded to 6 chlorides, right? 4 in the plane, 1 above, 1 below. Not only that, we're going to have a repulsion, and then another attraction here. And so the lattice is summing up all the attractions and all the repulsions and adding them together. So there are many bonds here, because an ionic bond is just the attraction between positive and negative. And so what we say is there's not one mole, we say there's a lattice of ionic bonds. If we have 1 mole of sodium chloride, we're going to have a lattice of ionic bonds. Well, all we have to do when we break apart this lattice is pull one of these ions away. So we got to break it free. Well, when we're looking at breaking it free, then the easiest is just to consider what we call a formula unit like this. How hard is it to break apart these ions? Well, it's going to be harder to break apart the ions in sodium chloride than it is in sodium bromide because, as was mentioned, chloride is smaller. And therefore, sodium chloride should have a higher lattice energy because lattice energy is breaking apart the lattice, right? Actually into the gaseous state. And so if I ask you which one is more stable, well, I would assume sodium bromide versus sodium chloride, I would assume that sodium chloride is more stable because it has a stronger lattice. Right? This is for the solid. And therefore, sodium chloride should be slightly less soluble. Both of these are soluble, but sodium chloride should be slightly less soluble. Sodium chloride should have a higher melting point because in order to melt it, you have to break apart the bonds, okay, etc. And so we could do the same kind of analysis here. It's calcium versus calcium. When we compare it, carbonate's a 2 minus, sulfate's a 2 minus. So the charges are the same, but the ions are different. Carbonate is trigonal planar, sulfate is tetrahedral. Sulfur is a little bigger than carbon, and so packing trigonal planar means they can't get as close, you know, versus this is more spherical. And so this is hard. This is hard. We have to really dig into the structure of this to figure out which one's more stable. And so rather than doing that, I mean, we could take some stabs at that. You know, this is trigonal planar. It's going to have a different packing arrangement, etc. What we might just do is we might just look for some factual evidence. If I wanted to look up factual evidence, then I might see, okay, which one is more soluble, which one's less soluble. You know, the one that's more soluble should have a weaker lattice. You know, it should break apart more easily, maybe, and the one that's less soluble should have a stronger lattice. And so one of the ways that we could resolve this is by looking at experimental data, you know, factual data. And so which one of these two is stronger? Well, let's consult data table. In the old days, you would consult a book like the CRC Handbook of Chemistry and Physics. The CRC Handbook of Chemistry and Physics is a big, thick book full of data. And then we'd look calcium sulfate versus calcium carbonate and see what difference in properties might give us clues as to which one's more stable. Or we could use the Merck index, you know, which is, Merck index is more biased towards biological and organic molecules. But actually, I'm going to do that later. But do we have to do that? Do we have to do that? Well, this one is a big question mark. And before I spend a lot of time looking up data table, is there some other driving force that might occur in here? And it's obvious there's one other driving force here that's readily apparent, and that is CO2, gas. All we need is one driving force, so we have gas formation. So it doesn't really, here, you know, I don't know, you know, how they're going to cancel each other out, but we have one more driving force, and that is sulfuric acid is a strong acid going to carbonic acid, or CO2. CO2 is also acidic. And so we're going from stronger acid to weaker acid. And so typically it turns out is if we have one driving force, even if we have this thing, which could favor calcium carbonate, we're still going to expect a reaction to occur. And so here we have two driving forces, stronger acid to weaker acid plus gas formation. And therefore, even though this is a question mark, I'm not going to worry about this. I'm going to say that there is driving force for this reaction, and the reaction should occur, rather than get into that. And so I can't use precipitate because I just don't know. All right, once I have this, I have the complete equation. I got to make sure it's balanced. It is balanced, and I got to write the states in. Aqueous you can leave off as long as you write all the other states. All right, so we see reaction should occur. So let me rewrite this. And the driving force is stronger to weaker acid plus gas formation. All right, once we have the CE, then we'll write the ionic equation. The ionic equation, you ionize the strong electrolytes. The strong electrolytes are the strong acids, strong bases, and soluble salt. So calcium carbonate's an insoluble salt, so we just leave that alone. There's the calcium carbonate solid. H2SO4 is a strong acid, so we ionize strong acids. So we have two choices. This can ionize into two H pluses plus a sulfate, or it can ionize into an H plus an HSO4 minus. Which one should we pick? 2 H plus and a sulfate? Unfortunately, that's the wrong choice here. We don't want this. Because what happens is one proton breaks off at a time. So when the first proton breaks off, we're left with H plus and HSO4 minus. Now HSO4 minus, is that a strong electrolyte? Well, what are strong electrolytes? Strong electrolytes are strong acids, strong bases, and soluble salts. HSO4 minus is not a strong acid, it's not a strong base, and it's not a soluble salt. So we leave it alone. So once the first proton breaks off, the second one does not break off 100%. And then calcium sulfate is an insoluble salt, so we just leave that alone. And then water is a non-electrolyte, or a very, very weak electrolyte, and same thing, CO2 gas. All right, for the net ionic equation, we get rid of spectators. And there are no spectators here that we can cancel out. And so the ionic equation and net ionic equation are the same thing. All right, let's do another example here. Well, this one is a complicated one, even though it really doesn't seem to be that complicated initially. It's just potassium sulfide. What's the formula for potassium sulfide? K2S. Potassium sulfide. And acetic acid. We'll use this way of writing acetic acid. This is an AB plus CD, double replacement. And so it's going to be potassium with acetate. Potassium with acetate is potassium acetate. And H with S. When we do double replacement or metathesis, you know, S is capable of accepting two H's, so we just go to reaction. And so do we do HS minus or do we do H2S? For metathesis, go all the way. And so we'll just take it all the way to H2S rather than leave it at HS minus. diprotic. So before we balance this, is there a driving force? Oh, potassium salts are all soluble, acetate salts are all soluble. There's no precipitate here. But H2S is a gas. We want to do this reaction in the hood. We mix acid with a sulfide-containing compound, you're going to generate the toxic gas, H2S. And so we have a driving force, gas formation. Is there any other driving force for this? Let me see. Well, one is acetic acid. Acetic acid is the acid we start with. What's the acid we end with? Well, let's take a look up here. This is a different way of writing acetic acid, CH3COOH, acetic acid. We start with acetic acid and we end with H2S. And so this is stronger acid, acetic acid, to weaker acid. They're both weak, but acetic is stronger than H2S. And so we can write another driving force for this. And that is going from a stronger acid, acetic acid, to a weaker acid. This is also a driving force. So no precipitate, like the last, well, the precipitate might have helped the last reaction. We don't know because we never looked up which one is more stable, you know, calcium carbonate or calcium sulfate. Here, there's no precipitate, and so we don't have to worry about that. And so that's a driving force. All right, now let's put in the states here. The state, this is aqueous, this is gas. Acetic acid is, all right, what about potassium sulfide? Potassium salts are all soluble. Since, you know, acetic acid is mostly water, typically we'd write aqueous here, but we can't. We can't write aqueous here. But we have to write solid. And what's the reason for that? The reason for that is because of one of these chemical properties of sulfide, you might recall. And that is, what I do is I treat this as a soluble salt. So K2S is soluble because all potassium salts, or group 1 salts, are soluble. And so if I have solid K2S, and I mix that with water, I'll get K2SAQ. But K2SAQ, this is deceptive because K2S, being a soluble salt, is also a strong electrolyte. And so a strong electrolyte means that K2S is going to consist of 2 potassium ions and a sulfide ion. And the problem is this. Here's my problem. You might have recognized that something about sulfide. Do you recognize something about sulfide? Sulfide, saw it before? Where did you see it before? It's a strong base. You guys haven't memorized the strong bases, right? Except for hydroxides, but there are others. And sulfide's a strong base. What's the strongest base that can exist in water? Yeah, sulfide is a strong base, more powerful than hydroxide. The strongest base that can exist in water is hydroxide. So that means that K2SAQ doesn't exist. It's impossible to exist, right? how can K2SAQ exist? If somebody asked you to grab a bottle of K2SAQ and you went to the shelf to grab, you wouldn't find it. You wouldn't find it because of this. Because strong bases do what in water? This is the problem, but it's easily fixed because strong bases ionize. Strong bases hydrolyze 100% in water. And so if we have sulfide, it's going to attack the water 100% to form, well, bases are proton acceptors. Water can go either way, so it'll be the acid. What will we form? All right, we have a choice. We could form HS minus or H2S. We form HS minus. We do not form H2S. Well, why did we form H2S over here? We formed H2S because in metathesis, we go all the way. This is what we call Bronsted acid base. For Bronsted acid base, only transfer one proton at a time. We're going to keep it. We're going to keep it simple right now. Then we'll get more complicated later. We just transfer one, and so it's going to form HS minus plus. What else? Hydroxide. And so this is going to happen 100%. We aren't going to get sulfide in water. We can't. Because the sulfide will attack the water to form hydroxide. And so in the ionic equation, this will be the complete. We take our solid, we put it in the water, and these are the species, the major species we're going to generate. We're going to generate KHS. No, actually, we've got to write it in ionic form. So 2 potassiums plus an HS minus plus an OH minus. And so if I took my K2S solid and put it in water, I'm going to have potassium ions, hydrogen sulfide ions, and hydroxide ions. This is, again, the leveling effect. And we're going to get acetic acid. Acetic acid is a weak acid, so we leave it intact. And then potassium acetates is soluble salt. Actually, I didn't balance it. We need 2 potassium acetates. We need 2 acetic acids. I forgot to balance. 2 potassiums and 2 acetates, and an H2S gas. This would be the ionic equation. The net ionic equation will get rid of the spectators. The spectators would be potassium ions here. And so the net ionic equation is HS minus. I'm going to get rid of the AQs. When I do that, I've got to make sure I put gas, liquid, or solid. I only have one gas at the end. So HS minus plus OH minus plus 2 acetic acids yields 2 acetates plus H2S. Now, this one is a very tricky one. You know, and this one's a tough one, basically. And it's tough because of the sulfide. You know, one of the chemical properties of sulfide is it's a powerful base. Powerful bases can't exist in water. Now, that's a soluble sulfide. If it was an insoluble sulfide, we treat it differently. And so the question is, why did we do it like this for potassium sulfide, but we left calcium carbonate in the previous problem? Do you remember calcium carbonate in the previous problem? Why didn't I break that apart? The reason calcium carbonate was left alone in the previous problem because it was insoluble. This happens to be soluble. And so we could start off with powdered potassium sulfide. And the powdered potassium sulfide is not powdered potassium hydrogen sulfide and powdered potassium hydroxide, right? That happened after it mixed with water. All right, one more. And actually, there are 2 more, but we'll just do one more. We'll call it a day. I don't know what happened. What did I do with the red? Okay, this one's lead. Actually, I typo here. This should be lead 2 iodide. What's the formula for lead 2 iodide? PbI2 plus hydrochloric acid, Cl. Another double replacement reaction, so this is good. All double replacement reactions so far. What are we going to form? We just switch the ions. So we got lead ions paired with chloride, PbCl2, and hydrogen ions paired with iodide, so we're just going to form HI. Now let's look for a driving force for this reaction. So looking at the driving force for reaction, chlorides, bromides, and iodides are all insoluble, except for silver, lead, mercury. So this is, are soluble except for silver, lead. So that's a precipitate. So can I say that the driving force is precipitate? Yes? But you have to be careful because this is Chem 1B. I start this in Chem 1A. This is not Chem 4. And PbI2, there's one problem with this, and that is PbI2 is also a solid. So we're sacrificing one solid for another solid. Is that going to happen? In other words, which one is a more stable precipitate? Which one's a more stable solid? PbI2 or PbCl2? Well, this one, you know what? This one, last time we tried to deal with it, but we didn't have to because there were other driving forces, right? And so this time I don't want to deal with this. Let's try to avoid this and see, is there some other driving force that we can use for this? Oh yeah, there is. HCl and HI, right? Which one's a stronger acid, HCl or HI? HCl. The HCl? Yeah, you're right. Well, I should, HCl versus HI? Oops, HI is a stronger acid. There's a reason for that. So HI is a stronger acid. Okay, HI is a stronger acid. So this is stronger acid, and this is weaker acid. And we'd like to go from stronger, which is less stable, to weaker. And so that means this is the more stable side. If this is the more stable side, then there should be no reaction, right? So are we good? No reaction? No, we're not good. Because what am I forgetting? What did I forget? Oh, no, I mean, yeah, actually, no gas formation here, so we'll eliminate that. I forgot the leveling effect. The leveling effect means that this is wrong because they're tied. Okay, now I'll look for gas formation. There's no gas formation. So that means the only way to answer this is to know which one is more stable. PbI2 or PbCl2? Which one is more stable? So I could go over here onto, I don't have a CRC, I don't have a Merck. So what I'm going to do is I'm going to go onto Wikipedia. Wikipedia is pretty good, actually. It has a lot of the data you'd find in the CRC. And so one of the things I can do is I can look at the solubility in water. All right. This is for which one? PbI2. we know PbI2 is insoluble, but how insoluble is it? And so people have done quantitative measurements. So for example, at 20 degrees C, you could dissolve 0.0756 grams in 100 milliliters of water. That's not much. In other words, you can dissolve 75.6 milligrams in 100 milliliters of water. That's PbI2. We go to PbCl2. The solubility at 20 degrees is 10.8 grams. So we can dissolve milligrams of PbI2, but in 100 mils. And so if this were 100 mils, we have to divide by 10. We could dissolve, in 100 mils, we could dissolve 1 gram or 1,000 milligrams here. And so which one's more soluble? PbCl2. PbCl2 is a heck of a lot more soluble, it looks like, than PbI2. So PbCl2 is a lot more soluble, meaning its lattice is more stable or less stable? Less stable. And so in this case, this is more stable. PbI2, this is less stable, right? But are you going to be able to look up Wikipedia on a test? And so you aren't going to be able to look up Wikipedia, obviously, on a test. And you aren't given the data on the test. I might give you the data. And so there are two ways to answer this question. A lot of the class will say you can't answer the question because we don't have enough data. Not enough information is given, so they'll leave it blank, right? So a lot of the class will write that, just leave it blank, can't answer. But a small percentage of the class will try to figure it out, you know, based on maybe things like a little bit of theoretical knowledge. And so if you couldn't look it up on Wikipedia, what would you do to try to figure out which one is more stable? What would you try to do? Yeah, you look at this, you know. They're both lead. And so what's the difference between iodide and chloride? What's the difference between iodide and chloride? The size, right? What's bigger, iodide or chloride? And so if I have lead, which is a +2, or 2+, and I have iodide, which is a minus, to break these two ions apart, versus if I have lead over here, which is 2+, same size, let's say, and a chloride, like this, what's going to be harder to pull off, a chloride or an iodide? Or what would be harder to pull off, the lead from iodide or the lead from chloride? And so what we see is this. We see that the charge is more dilute here. The charge is more concentrated here, the electron drop. Same number of dots because they're both the same charge. And so what's going to be easier to break? Which bond will be easier to break? This bond will be easier to break. If this bond's easier to break, that means the lattice is weaker. If the lattice is weaker, that means it should be more soluble, right? More soluble. But is that what was observed? No, it turns out lead-2 chloride is a heck of a lot more soluble. And so what does that mean? Does that mean everything I've talked about so far is wrong? Does it? No, it means I'm oversimplifying bonding. Because we have to really, in order to understand bonding, we have to understand bonding theory. And when we understand bonding theory, you know, how is a bond made? What is an ionic bond? How does it differ from a covalent bond, right? And so bonding is very important in understanding, structure and stability. And this is why I want you to go back and review bonding. The reading load at the beginning is not high because we aren't covering any chapters. You're just doing this from the PowerPoints. And so you should use that time to reread some of that stuff from Chem 1A. And so do you know the reason why what I just told you doesn't work? Well, what's going on with Coulomb's law? Is Coulomb's law wrong? No, it's not wrong. It's because I've way oversimplified the bonding. And you know I've way oversimplified because of this. PbCl2 is insoluble. This is lead 2. But lead 4, PbCl4, is soluble. Wait a minute. This is lead plus 4. This is lead plus 2. Why is this soluble? This one insoluble. It doesn't make sense because a plus 4 should be a heck of a lot more attractive for an anion than a plus 2. And so what's the answer to this? The answer to this is this. This turns out to be ionic. This turns out to be molecular. In other words, the bond here is much more ionic. The bond here is much more covalent. Do you guys remember, I think in chapter 9, there was this chart, graph. The graph was percent ionic character, I think it was chapter 9, versus delta En, the difference in electronegativity. And the trend was something like this. And you had some data here. So the bigger the difference in electronegativity, the more ionic it is. But what we should notice from this is that the bonds, the two extremes of bonding is covalent bond to ionic bond. And it's not one or the other, it's a mix. So you're going to have a percentage of ionic character, all the way up to 100%, all the way down to 0, but it could be like 50% ionic, 70% ionic, 80% ionic, 20% ionic. And so the level of ionic, when we're doing this with attractions, this works beautifully if the bonding is 100% ionic. If the bonding were 100% ionic, then for sure, lead 2 chloride would be less soluble, not more soluble. Right? But the bonding, especially for these heavy metals, has a high degree of covalent interaction in there as well. And so that alters things. And so we can't oversimplify it. And so the point is this. The more you know about the theoretical stuff, the better it can serve you. But even if you know a little bit, let's say we're just going to go based on this, then what's better, a blank page or somebody saying that, well, chloride is smaller than iodide, therefore I expect a stronger lattice here. And so if you say that you expect this to be a stronger lattice and we expect reaction to occur, that's pretty good because at least you're analyzing it. You just missed the part about the covalent bond and the ionic bond, but how can you gauge that? It's tough to gauge. And so what you can say is based on arguments, assuming that the bonding is ionic or 100% ionic, then we should expect reaction here. And so what you can do is this: if you're ever given a problem in which you need more data, more information, never write an answer like not enough information to solve. It's much better if you just try to solve it and just make some assumptions. We'll assume that the bonding's ionic, therefore we're looking at charge species attraction, Coulomb's law type interaction. Does that make sense? Okay. All right, we'll stop here, and then we have one more reaction to go. But this one is a tough one because of that. Let me give that to you tomorrow. It should be no problem. Oh, you know what, Monica? I did bring them. I thought I left them in the office. Do you want it today?
All the homework is handwritten, right? We don't use mastering chemistry.
I'm gonna make a mastering chem
Oh, okay.
site. You could use that just for help, but I'm not gonna grade it.
Oh, okay.
Oops.
Are you gonna give us a code later?
Yeah. Yes, did you check it already?
Yeah, I had took it in the spring, but I withdrew because I was working.
All right. Yeah.
But, yeah, I just wanted to make sure it was all handwritten.
Yeah.
Can I get an ad slip to add into the class?
Well, actually, since she was here
Yeah, there's one
first,
person, but there's
yeah.
like 5 spots online.
Yeah, they're actually.
Unless the online isn't correct, I'm not sure. I'm just like reading on base what's not what was online.
Oh yeah. And so you missed yesterday because of
I was waitlisted for another class.
which class were you trying to take?
I was trying to take a bio class.
A bio class?
Yeah, but it doesn't look like I could get in because everyone. Yeah, long story short, I don't think I could get in. That's why I was going to try to do this one.
And when did you take Chem 1A?
I didn't. I already have a degree. I'm just taking some classes for medical school, so I didn't take 1A here. I took
1A somewhere else?
Yeah, I took a general chem.
Where did you take it? Or,
UCLA.
Which?
We have it's called a 14. We have it's 14A, 14B, 14. Yeah, it's 14A and 14B. So it's different.
Did you complete both of those?
Yeah, but I have to retake this one.
And then 14C is what, the biochem?
No, 14A and B is general chem, and C and D are organic chem.
Okay, so I
have to take the second general chem.
Okay. So A and B are just like.
It's equivalent to like 1A and 1B here.
And then what about do they still have the 11A, B, C at UCLA, or they don't?
They don't have anyone.
And so it's upper division now for the other ones?
We don't have a Chem 11. The 14 is the
lowest. Okay. All right. And how long ago was that?
That was 3 years ago.
Oh, okay. So it's still fairly fresh. Do you have to take 1B though, or you're just taking
Yeah,
for
I have
review?
to. No, I have to take it to replace a grade.
Oh, okay. But A and B were okay then?
Yeah, A was okay. B, I'm replacing. That's why I'm taking. That's why I'm trying to take Chem 1B, the second gen.
Okay. And what did you guys cover in A? Because UCLA does it backwards. You know, UCLA normally because I was at UCLA, and so UCLA does the equilibrium first, the 1B first, and then the 1A second. Most UCs do it that way. They do it in reverse sequence than what we do.
I have it with me. Let me check.
And I was just waiting for an ad slip as well.
Could you register online
It says that's why I came to class. It says it needs.
You missed the first day.
No, it won't let you register regardless. It says it needs your consent. So I'm assuming.
I can't. You're talking about the prereq, right?
No.
They're blocking you for the prereq.
I have prereqs already.
You have it already taken out?
Beforehand in advance.
Then you should be able to register.
No, it won't let you because it says it's basically you can't register because they stop registration for you can't add without an ad code basically.
Oh, because you're
because that happens
late.
to all classes. It's not just yours. It's other classes. I'm still trying to walk on as well.
Okay.
But let me double check. The first one was equilibrium, acids and bases, and the second one was thermodynamics, electro something, and then kinetics. So how does it work here then?
We're doing equilibrium.
You guys are doing equilibrium.
Yeah.
What about acids and bases?
We're doing acids and bases, equilibrium, and kinetics.
And kinetics.
Thermodynamics is Chem 1A, and quantum is Chem 1A. Do you have? I mean, does it have the
It just says
descriptions?
abbreviation. I have to follow. I have to look it up.
Well, if you take a look at the syllabus, then you can see. It depends because if you're preparing for the MCAT, right? Is that it? You're preparing for the.
Well, to get into med school.
Okay,
Not just
so
MCAT, just in
Yeah,
general?
in general to get into med school. But then if you, well, it depends. Um, Usually what they do, this is when I was at UCLA, they did the equilibrium first, and so that would be 1B, and then they did the 1A part second. But listening to what you just described, it's mixed up now. And so what's going to happen is you're going to have some covered, so the equilibrium stuff you probably already heard, and then some of the other stuff you're going to miss because that's in 1A. And so you should take a,
Should I start with 1A then?
that's weird.
Or why would it be like flipped?
Because they're two philosophies for teaching general chemistry, and so there are two versions of books. Like if you have one author, they have two versions of books. They have the atoms first version and then the equilibrium version. And so UCLA has this kind of equilibrium. They start off, well, at least when I was there, they did the equilibrium and then they did the atoms, which is just the opposite of what I had when I was a student. Yeah, and so it depends on what you're after. If you're just after credit, then just 1B is fine, you know? But if you're after hitting some of the topics you might have missed, or, you know.
Well, I want to like as a review for MCAT and for like.
Then you might want to take both, 1A and 1B simultaneously, you know?
Okay.
Well, maybe, I don't know, or just sit in on 1A, you know?
I'm trying to find out the complete.
For credit, I don't think they care, you know? I don't think they look at the topics that carefully. We do thermodynamics, some thermodynamics in here too.
So maybe they both cover, but that's probably a good recommendation to do both. Do you guys offer 1A and 1B in the spring, or is it just you guys offer every? So it's like I could even flip it, right?
Yeah.
Does it like? I know you're making a lot of references to like 1A. Does it matter if I flip it around? If I do 1B first and 1A, would it like?
No, it wouldn't matter, but that means you're missing some 1A stuff. If you're missing some 1A stuff that was covered in whatever.
I think that it was better for me to start on 1A then. Take them concurrently.
Well, I don't know. I mean, you could just review it on your own. Like all this stuff. I've been talking about things to review since yesterday. Oops.
Are you still recording?
Oh, I'm sorry.